Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about solid mechanics and materials subject. So in this subject, today, I want to discuss about Euler's column theory. So in this, we will see how to derive the Euler's column theory. So what is this column theory? And then how to calculate stresses by using this Euler's column theory, and what are the various conditions are there in column we will analyze in this topic. So before going to enter into the main topic, so the outcome of this topic is we should know to analyze the Euler's column theory and deformation of columns under and struts under various loads. Whenever the load is acting on these columns, so how to react these columns we will see. So that at the end of the course, after completion of this topic, the student should be able to analyze the deformation of the columns and the struts under various loads. So the Euler's column theory, first of all, we'll see the introduction point. A structural member subjected to an axial compressive force is called a strut. A structural member subject to an axial compressive force. So this is a structural member example, and the axial compressive force is acting, it is said to be strut. As per definition, the strut may be horizontal, inclined, or even vertical. So the strut may be horizontal also, and the inclination also strut. Example, connecting rod, piston rod. In our mechanical engine, post-torque engine, we can see the connecting rod and piston rod. But a vertical strut used in buildings or frames is called a column. The vertical struts already shown in this diagram. These types of struts are called columns. The filler between roof and floor. The long vertical strut is nothing but column. The short one is called as a strut. It may be horizontal or inclined or vertical. So how these columns or struts fails under loads? So what is the criteria for failure of a column or strut? So it has been observed that when a column or strut is subjected to some compressive force, then the compressive stress induced. So so whenever the column or strut are subjected to some compressive force, there will be a compressive stress induced. Suppose example, this column. So the compressive force is acting. So due to this compressive stress will be developed. So what will happen? The diameter will be increased and the length of the column will be decreased. At the same time, the compressive stress induced inside the column. So that is compressive load per area, where P is compressive force and A is cross-sectional area of the column. If the force or load is gradually increased, the column will reach a stage when it will be subjected to the ultimate crushing stress. So whenever the gradually increase the column, the load will be reach a stage when it will be subjected to ultimate crushing stress. That stress is called crushing stress. Beyond this stage, the column will fail by crushing. The load corresponding to the crushing stress is called crushing load. Whenever the column at which column fails due to load, that load is called as crushing load. The corresponding stress is called as crushing stress. When it happened, so whenever the force or load gradually increases the column will reach a stage, that is the ultimate crushing stress, the maximum point. Already we have studied in stress strain curve. A compression member does not fail entirely by crushing, but also by bending. So, not fail due to compressive stress. Sometime the bending also will occur. I will show you the actual diagrams. So that is, this phenomenon is called as buckling. So this happens in the case of long columns. The long columns, this type of buckling will be happening. So all the short columns fail due to their crushing. But if a long column is subject to take compressive load, it is subject to take compressive stress. The short columns fail due to their crushing only, not bending. The short columns only crushing. Whenever the compressive force acting, the crushing due to this load. But in the case of columns, the buckling, so bending also occur. See, the failure of column or strut, the actual the columns here shown, our building column. So this is column. It is a vertical column between pillar and floor, roof floor. See how it bends here. So due to the compressive load, crushing and also bending. See in this diagram. So it will fail due to crushing load. Why? Because the load is reached ultimate stage. Beyond this ultimate crushing load, so the column will fail. So if the load is gradually increased, the column will reach a stage. So that stage is called as buckling stage, when it will start buckling. So the load at which the column just buckles is called buckling load, at which the column just started to buckling. That load is buckling load or critical load or crippling load. And the column is said to have developed an elastic instability. For a long column, the value of buckling load will be less than the crushing load. So the buckling load will be less than the crushing load for long column case. So moreover, the value of buckling load is low for long columns and relatively high for short columns. See the here shown this the column failure, buckling and compression and shear. This is buckling happened in the long column, in the short column compression and shear. See the original the buckling fail of the column you can see in this figure. So now, up to now we have seen what you mean by column and strut and how it fails. We have discussed. Now, so what is this Eulers theory? To avoid this failure, the Eulers derived one theory. That theory is called as Eulers column theory The first rational attempt to study the stability of long columns was made by Mr. Euler. He derived an equation, the buckling load of long columns based on the bending stress. While deriving this equation, the effect of direct stress is neglected. This may be justified with the statement that the direct stress induced in a long column is negligible as compared to the bending stress. In long column, the direct load is avoided. The direct stress already know compared to load for area. For this is neglected. Why? Because when compared to the bending stress, this value is very less. So he has derived based on these assumptions. So what is the first point? The following simplified assumptions are made in the Eulers column theory. Initially, the column is perfectly straight, and the load applied is truly axial. The only axial load, the axial load that is parallel to the axis of the column, and the cross section of the column is uniform throughout its length. So the column material is perfectly elastic, homogeneous, and isotropic, and thus obeys Hooke's law. So the assumption is the column material is perfectly elastic, homogeneous, and isotropic, and also it obeys Hooke's law. Already you know Hooke's law, the stress is directly proportional to strain. The sigma E is equal to E into epsilon. So the length of the column is very large compared to its cross-sectional dimensions. So the cross-sectional dimensions, so this is the diameter and the length. The length is always very large when compared to the other dimensions. So the shortening of column due to direct compression being very small, that is neglected. The failure of column occurs due to buckling only. The failure is of the column occurs buckling load. So the sign conversions are important in this theory, though there are different signs used for the bending of columns in different books. But yet we shall follow the following sign conventions which are commonly used and internationally recognized sign conventions I have taken. So the positive sign, this shows diagram. So whenever the column bends like this, and the negative sign, and then is the convexity diagram, convexity shown here in first case, and second case concavity, the concavity shape and the convexity. So types of end conditions are very important in these columns. So actual practice, there are a number of end conditions. For columns, we shall study the Euler's column theory on the following four types of end conditions, which are important from the subject point of view. One is both ends hinged. Second one is both ends fixed. The third one is one end is fixed, other end is hinged. And one end is fixed and other is free. So these are the conditions 1, 2, 3, and 4. 4 conditions are there. So now we will consider first one, both ends are hinged. So consider a column AB of length L hinged at both of its ends, A and B, and carrying a critical load at B. So as a result of loading, let the column deflect into a curved form AX1B, that I will show you the diagram. Now consider any section at say X at a distance X from A. So this is both ends hinged. and B hinged and A also hinged. The length of the column. Here, the P is a critical load on the column and Y is the deflection of the column at X. So take X. So consider any section, cross section X at a distance X from the A. From its point, the distance is X and the cross section is X. So the moment due to critical load is P into Y, the deflection multiplied with critical load. So here minus sign used. Why? The minus sign due to the concavity towards initial center line. The initial center line concavity shape. Already I show you. We have discussed about this negative sign. So this is concavity sign. So the columns with both ends hinged. Here we have calculated moment due to critical load and then apply the bending equation. So that is EI into d square y by dx square plus P into y is equal to 0. So this is the stress sigma B is equal to the moment due to the critical load. So already we know that is P into y, the sigma B have derived in the bending stress equation. So EI into d square y by dx square plus P into y is equal to 0. So d square by y into d divided by dx square plus P by EI into y is equal to 0. The auxiliary equation we can write like this, and the m is square root of minus P by EI. So we can take the m is equal to plus or minus I, the complex number, I into square root of P by EI. So we can write the roots alpha plus or minus I. The general solution of these complex numbers e to the power of alpha x into C1 cos beta x plus C2 sin beta x. But here C1 and C2 are constants. You have to calculate this value by using boundary conditions. So therefore, the y is equal to C1 cos x into square root of P by EI. What is this P by EI? M. Plus C2 into sin x into square root of P by EI. So this is written as equation 1, where C1 and C2 are the constants of integration, the values of constant obtained by substituting initial values, boundary conditions. We know that when x is equal to 0, y is equal to 0, the values are substituted x is equal to 0 and y is equal to 0. X is equal to 0 and y is equal to 0. So when x is equal to 0, entire term changed into, converted into 0, cos 0 and sin 0. So here the cos 0 degree and sin 0 degrees. Now the C1 is, cos 0 is 1, so C1 is equal to 0. Similarly, when x is equal to L and y is equal to 0, the consider when x is equal to L and then y is equal to 0. To substitute these values in the previous equation, we will get one more equation. 0 is equal to C1 into cos L into P by EI. So in case of here, in place of x, you have to substitute L and then y is equal to 0. So that we will get the final equation C1 is equal to 0 and C2 value we will get from this equation. the C2 is equal to 0 or equal to 0. So now if you are consider C2 to be equal to 0 as also C1 is equal to 0. So it indicates that the column has not bent at all values and bending of the column with 0, but it is not true. The sign L into square root of P by EI is equal to 0 and L into P by I for pi values 0, pi, 2 pi and 3 pi. So taking the least significant value. So that is L into square root of P by EI is equal to pi. Now you can write the P is equal to, so you can squaring on both sides, L square into P by EI is equal to pi square. So P L square is equal to pi square into E into I. So P is equal to pi square E I by L square. This is the crippling load or buckling load. Crippling load or buckling load or critical load. So at which the column bends, that corresponding load is called as buckling load. The corresponding stress is called as bending stress. So this equation is said to be Euler's column theory. So I is, the moment of inertia, E is Young's modulus, and the length of the column L. So the P is equal to pi square E I by L square. So like this, you have to derive the Euler's column theory. So we have seen in first case, so both ends are hinged. Next in section, both ends fixed. So how to derive? And then one end is fixed, the other end is hinged, and one end is fixed, and other end free. We will see in next sessions. So the references are taken as S. Ramamrutam. So title of the book is Strength of Material, and one more book is R.K. Bansal, Textbook of Strength of Materials, and R.S. Kurmi and Gupta, Strength of Material. These are the references I have taken for this PPT. So you can refer any one textbook for more information. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.